updates. We just finished the midterm exam. So then next we need to prepare for the final. Yeah. So this week, next week, then the final week. So we only have the last 3 weeks for the remaining of the semester. Yeah. So let me give you the remaining assignments for the last 3 weeks. After this class, I need to give you 2 assignments. One, project number 2, our second programming projects. Yeah, because I need to give you approximately 3 weeks. Yeah. So let me look at the calendar. Yeah. The calendar today, 20th, July 20th. Yeah. And then, because after 3 weeks, we will, all right, yeah. So after 3 weeks, so today, 1 week, 2, yeah. So we're pretty much near the end of the semester. Yeah. All right, yeah. Look at the August, yeah. Approximately 3 weeks. Yeah. So I may set the deadline of the project number 2, August the 9th. Yeah. August the 9th. Yeah. Because these 4 days, the final period, final exam period. August the 5th through August the 8th, Saturday, these 4 days, the final exam period, all right? Yeah. Then I set a deadline for project number 2, August the 9th. Yeah, about 3 weeks. Yeah. Slightly less than 3 weeks, yeah, but that's the maximum amount of time we have. All right, yeah. Then I also, so that's today. Tonight I need to post this assignment. Tomorrow I need to post second homework assignment. So you need to practice for the final exam. So tomorrow, Tuesday, I need to post second assignment. All right. Then let me see. I need to give you, plenty of time to complete it. Yeah. So still this Sunday, August the 2nd Sunday, that's the deadline. Okay, that's the deadline for the homework assignment number 2. Yeah. And homework assignment number 2, I will do in this way. Yeah. So let me, write something here. Let me play the PowerPoint slides here and write something here. All right. Remember, each assignment we have 3 parts, right? Part A, Part B, and Part C. Yeah, 3 parts. Yeah. So homework assignment number 2, I will do it slightly different from homework assignment 1. Yeah. Yeah. Yeah, because I want to reduce your work a little bit. Yeah. Yeah. So I basically, the only question for the in-person comprehensive, not comprehensive, all right? Are we going to receive similar format? A similar format to the midterm, but all completed on paper. No, let me explain your question. Yeah, all right. So let me finish homework assignment number 2. So then I get back to your question. All right. Homework assignment number 2, normally we have 3 parts, right? Parts A, B, C. You know those 3 parts. Part A, concept question, 10 concept questions. Part B, 10 basic computation questions. And part C, 5 challenging questions. In that setting, the same as before. But near the final period, usually you have too much work to do. So I want to reduce amount of work as much as I can. But at the same time, we still need to cover the things we need. Under that condition, I try my best to reduce your workload. For that consideration, part A, the same as quiz number 4. So we need to do quiz number 4. Okay? Yeah. So, but that's the same thing, same assignment part for part A of homework assignment number 2. Okay? All right. Then, tomorrow, Tuesday, I will post 15 questions for part BC together. Okay? BC together. But homework assignment part BC, I do not need to include concept questions. So because it's already in homework assignment number 4. So in this way, reduce your workload a little bit. So then for the final exam, now I get back to notice question. Yeah, final exam. So you know the period, right? The testing period, August 5th through 8th, right? 4 days. Yeah. And August the 5th. Wednesday, right? Yeah. August 5th, Wednesday. Thursday, Friday, Saturday. Yeah, because this is Saturday. Yeah. So this is Wednesday. All right? Yeah. First, not comprehensive. Okay? Yeah. So not comprehensive. Yeah. Only module 4 and 5. Last 2 modules. Yeah. No specific questions from first 3 modules directly. Definitely the knowledge of the first 3 modules will be used, right? So when we work on the questions of last 2 modules, but no direct questions from the first 3 modules. Yeah. All right. That's one. But another thing regarding the format, still 3 parts, right? Yeah. Parts A, B, and C. Yeah. Part A, 10 concept questions. Yeah. So that's the, only completely on paper, not completely on paper, all right? Yeah, because part A not on paper. Okay. Part A, online. 10 concept questions. Concept question online as quiz number 5. Yeah. As we use it the same as quiz number 5. So we try to merge, try to combine the assignments to reduce your workload. Yeah. And another update, other than quiz number 5, no quiz number 6. Yeah. In my original syllabus, I may put the quiz number 6, but I want to skip quiz number 6. Right. So when I calculate your average overall grades, I still drop the 2 lowest. Although we have 5 quizzes, I still draw 2 lowest scores. I keep the 3 highest scores, but then I just, using the scaling method to stretch it to 4 quizzes, right? Yeah. So because our original plan, we need to use the scores of 4 quizzes. Now we skip 1, but we need a percentage of 4 quizzes, but I just scale it. Yeah. So that's the way we take care of the quiz part. Then, final, in the classroom, okay? This part B, 10 basic computation questions. That's you need to do in class. In 2 hours. Yeah. Our official test time. Yeah. Only 10 basic computation questions. Okay? Yeah. Now part C. Part C also online. Part C, challenging questions. We know usually relatively harder, so you need more time. More time, so you need to do it online. Online, and the deadline is August 8th, Saturday. That's the deadline. Yeah. And the deadline for part A also August 8th. Yeah. So that's all you need to do. So you need to do some mental preparation in your mind. Yeah. So do the final push for the final. Yeah. Try your best for the final. Okay? Yeah. So that's, my clarification. Yeah. All right? Yeah. So any question, just let me know. Okay? Yeah. So now I do the lecture part. But if you come up with any questions, you just type in the chat area. Okay? Yeah. So when I see it, I will answer your questions. Yeah. All right. Yeah. Let's start today. Yeah. Today, first I do one topic. So that topic, because in our questions we need to use this result frequently. Yeah. Actually, in our first homework assignment, also in our midterm, the last question, first homework assignment, question number 24, we use part of the method related to this question. So here I want to give you the whole question. I explain the whole question, yeah. Because later you have pretty good chance to see the similar questions. All right. Yeah. So this question, find the second largest element in an n element array. All right. So question. Oh, yeah. Yeah. Very sensitive thing. Yeah. All right. Question. Find the second largest element in an n element. All right. You know, we assume distinct. Okay. Yeah. All right. Distinct elements. All right. Yeah. All right. So there is a formula, but I want to go through the whole solution working details to give you a better understanding. All right. This one, we apply the tournament method. And when we apply tournament method, so we run a complete tournament method. All right. Yeah. Yeah. Not just the one round, right? Yeah. Because in our max and min, finding both maximum minimum, we just run one round of tournament method. Then we stop, yeah, because that's enough. But here, we need to run a complete tournament method. So, what do you mean complete? Because we need to get a max. Yeah. We need to get a winner, right? Yeah. Yeah. Championship game, winner. Yeah. All right. Yeah. But at this time, the number of elements n, so this n number is a general n number. General positive integer, not necessary power of 2 number. Because power of 2 more convenient, right? Yeah, power of 2. The tournament method, when people apply, the best case scenario is power of 2. Like this past World Cup football. So in the tournament round, they selected 22 teams. Sorry, not 22, 32. Yeah, 32 teams. That's a power of 2. Yeah. So people like to use the best convenient number, power of 2 here. Yeah. But for us, we need to solve the general array problem. So we cannot make this assumption. No. Yeah. So we have to use the general n number, but when you use the general n number, the situation will be a little complicated. So you need to prepare to deal with the complexity of the general non-power of 2 structure. Yeah. All right, so here we need to do some abstract thinking really regarding this non-power of 2 thing. Yeah. All right? Yeah. So here when I draw diagram, I may draw some vague diagram. Yeah. Because it's hard to draw accurate diagram. Yeah. Because I may not get the perfect pairs, right? Yeah. For all rounds. Some of the rounds, we may have one player who cannot be paired. So that player will move to the next round directly. So that kind of situation we need to factor in. Yeah. All right. Yeah. So we just do the maximum number of pairs All right, yeah, and so on. Okay, yeah. So all right, yes, all the way. The last one, paired or not, we may not know. So here I just put there. Okay, yeah. If no pair for the last element, then this element moves to the next round. In that way, all right? So then, round by round, yeah, comparison, round by round, at the end, we know there is the, final winner. And we know that's max. Okay, all right. Now, the first question. How many comparisons? Do we need to get this max element? Yeah. Yeah. We need to add up all the comparisons for all rounds. Yeah. Although we have a lot of uncertain, comparison information for some of the rounds. But we need to ask this question. How many comparisons do we need to get the championship? Only championship. Not second largest, not third largest. No, only championship. Champion. Yeah, only champion. Yeah. All right? Yeah. Yeah. So can you have some idea for this question? Yeah. For this is our first question. Yeah. All right. Answer n-1. Sounds familiar? n-1. Yeah. That's one of our previous questions. Finding the maximum with n elements, we need an n-1 comparisons, right? Yeah. Here, the same thing. Yeah. Finding the maximum in an n element array. Although we arrange our comparisons in this tournament style, but the result is the same. Yeah. No matter how do you do the specific arrangement, the final result, the number of comparisons, should be the same. Why? So you can use the elimination thinking to understand this. Because each comparison, one player is eliminated, right? For each comparison, exactly one player is eliminated. At the end, we want to eliminate n-1 players. So the total number of comparisons must be n-1. So in this way, even with quite some uncertainty in the middle in our arrangements, but we don't worry. We can keep track of the data. So you can see by this elimination approach, we can keep track of the data, and we know the final number of comparisons in this round is n-1. Right? That's the first step. Second step. all right. Or round 2, okay, yeah. The first round 1, round 2, okay, yeah. This round, we need to target the second largest. Yeah. To target second largest, we use the similar idea we use in our homework assignment number 1, question number 22. Yeah. So we need to recall this question. Homework assignment 1, question number 24. Yeah. This one. The thinking, the logic. All right. So we need to look at the candidates. All right. So we need to consider the candidates for the second largest. Okay. How do we make a new group of candidates for second largest? All those elements that are qualified for the second largest element, we put them in a group as the candidates for the second largest element. Okay, all right. So the qualification, yeah. So we saw that before. So this time, we just need to, recall it. Yeah, recall it. Yeah. So that is the direct loser losers to the max. Must be direct losers. Indirect losers, no. They are not qualified for the second largest element. Must be direct losers in each round. Yeah. Each round. So let's say in each round, there is only one direct loser to max. Yeah. Because the champion only needs to play against one player in each round, then move to the next round, and so on. Yeah. So only one direct loser we need to count for each round. So that observation, simple observation we need to make. All right. As a conclusion, number of direct losers, we know, to max equals number of rounds of the tournament. Tournament of an element, right? Yeah. N. Yeah. How many rounds we need to play in this tournament? That number is the same as the number of direct losers. Yeah. So now we need to calculate how many rounds. So this time, because some information here, because some, vague part. So in our diagram, so this vague part related to this number of rounds information. So we need to get through it. All right. Because this n number is very general. Each round, sometimes we have even number of players, sometimes we have odd number of players. So these two cases, very hard to control. So we don't know when we have even number of players, when we have odd number of players. The situation could be very complicated. Right? Yeah. So in this relatively hard situation, so we need to put a lot of effort in our thinking. All right. The first step of our thinking, we look at the best case. What is the best case scenario? What is the best case scenario? N is power of 2, right? The best case scenario. So although our goal, we need to consider the general N, but we can start with the best case scenario, right? So we did this many times before. So in our thinking, nobody can stop us to do it this way, right? We are allowed to do it in this way. Golden rule, right? Remember golden rule? We can modify the original question to make it easier for us. That's the golden rule of problem solving. All right. Now, when n is a power of 2, the answer is straightforward, right? K. When you have 2 to the k number of elements, you need to play k rounds, right? K rounds. So the answer is so simple. You need to play k rounds. And how do you write k in terms of n? How do you get k out from n? Log base 2 of n, right? So that's the way you get this k number. The number of rounds, but it's for the best case scenario. So not our general case. So our next step, we need to extend it to the general case. So for the general n, what is the right formula to calculate this number of rounds? The general case, this number of rounds must be an integer, right? Must be an integer. But this log base 2 of n may not be an integer, right? We know. In general, it is not an integer expression. So can we do some modification on this expression to make it an integer expression, right? We did this kind of thing a few times before, right? By taking two special functions. One is floor function, another is ceiling function. So there are two ways we can use. One is we apply floor function Another is seeding function on this log base 2 of n. So which one you feel is the right way? Floor function way you feel the correct way, or seeding function way you feel it's a correct way? Yeah. Right? Yeah. Definitely. Yeah. It's easy to see that. Yeah. So number of rounds should be seeding function. Yeah. Why? Yeah, it's very easy to see, because when there is a singleton element, it moves to the next round without play. Singleton element is not eliminated from competition. The singleton element still has a chance to move to the next round. That means this decision shows us we should do the rounding up operation. Yeah. Because we have a few elements moving to the next round without play. Yeah. So round it up. That's the round it up behavior, phenomenon, right? Yeah. So naturally, the number of rounds should be seeding function of log base 2 of n. Okay? All right. Now, we are ready to calculate number of comparisons for the second largest. Comparisons in the second round. Yeah. Because if I say second largest, we need to look at the first round, right? Second round. In the second round, the total number of elements of the candidates, this many, there are this many number of direct losers to the max. So we need to find the largest number in these elements, minus 1. Minus 1. Yeah. So our formula, finding the maximum, we need a total number of elements minus 1. Total number of candidates for the second largest minus 1. So that's this formula. All right, now we combine both rounds. First round, second round, combine. So the total, first round n minus 1, second round minus 1, right? Yeah. So the final formula, so let me move here. The space here, final formula, n plus seeding function log base 2 of n minus 2. This is the formula. Finding second largest. This is the formula. Okay? Yeah. And another result about this is, and this is optimal. This formula is optimal. Yeah. We need to prove. Yeah. It can be proved, but it is pretty hard, but it can be proved. Yeah. I saw it in a textbook, so not our textbook. Yeah, so in a different textbook. The textbook I used before. Now, I used a long time ago. Okay, so there is a proof in that book. Yeah. this formula is optimal. Okay, yeah. All right, so that's this useful result. Yeah. So later when you see similar questions, so you can apply this result directly. Yeah. Also the thinking we used. Yeah. All right. Yeah. Now let's move to part C of module 4. Yeah. Because the homework assignment number 2, after this part C, you can do almost all the questions. Part D, I only give you one question in the homework assignment number 2. So one straightforward, a simple question in part D. So all other questions, relatively hard questions, covered in part ABC. Yeah, ABC, module 4, ABC. Yeah, cover 14 out of 15 questions. So there are 15 total questions in homework assignment number 2, part BC. Yeah, part BC, 15. Yeah. But the part D, only one question. Relatively simple, one question. Yeah. All right. Yeah. So now let me move to part C. Another big part of module 4. All right. Get it out of this presentation. All right. Then bring up part C. Mergesort. All right. All right. Now, C.1, Introduction to Mergesort. All right. So this part, we will learn another sorting algorithm. All right. And this one has some special properties. All right. First, we need to understand why we need to learn this special sort. All right. Problem number 15, merge two sorted arrays. Each array already sorted, ordered. We have two ordered arrays. You have seen setting, this kind of setting in our homework questions, right? Yeah. So the last few questions, you have seen some partially ordered subarrays, right? Yeah. So sometimes we need to merge them. Here, the original question, given two ordered arrays, how to merge them to get an ordered array? That's a simple question. So this operation will be the key operation when we do the merge sort. This is the merge operation. But first, I want to use a simple example to show you, the motivation part, why this operation is useful. All right. Yeah. Here, I consider a special example, very special. So, some kind of let's imagine we have this kind of a real world problem we need to solve. So what's that? We need to sort a huge, so here, still sort. We know how to do the sorting. But the data is quite special. The data size, huge. How large is huge? Here, I need to give you some important probably regarding the data size, how large it is. All right. Here I use this big line segment to represent the size of this whole array. All right. It is so large that you cannot load the whole array into your computer main memory. So you know, when you write a program to do the sorting, the first thing you need to load your array into the main memory, right? Yeah. The operating system needs to load the data into the main memory. Then your program instructions can process the data, right? Yeah. But here there is a big technical problem, because your main memory, your computer main memory, there is a limit on the main memory, right? Yeah. Several gigabytes, right? Yeah. For example, 16 gigabytes, 32 gigabytes, 64 gigabytes, right? Yeah. So you can look at the size of your main memory. Yeah. All right. So there is some size, but here you can imagine, yeah, under some special situation, your data is larger than the size of your main memory. Can you still sort the data? Right? Sort the array? Yeah. 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 The answer is yes, we can do it. But we need to do it in a special way. Well, we can solve the problem, but you have to do it carefully in a special way to get your huge array sorted eventually. Yeah. So what you should do, yeah, here, let me show you what should we do in this situation. Yeah. All right, divide and conquer, right? Yeah. The title of this module, divide and conquer. So we will do it in a divide and conquer approach. First, we divide this huge array into many smaller subarrays. Yeah. So each line segment represents a smaller subarray. How small? Small enough to be loaded into the main memory. So now, after the divide step, each array can be loaded into main memory without any problem. Small enough. Okay? Yeah. All right. Then in the first step, we can sort each subarray, right? Yeah, because we can load it into the main memory. Then we apply appropriate sort to get it ordered, get it sorted in main memory. Then we export it. Yeah. So we import data. After sorting, we export it to the hard drive. Yeah. Because the original data is on the hard drive. Yeah. The permanent storage of the original data is on the hard disk. Yeah. All right. So data. So this data state on hard disk. We know the hard disk has much larger size than the main memory, right? Several hundred gigabytes or even T. Yeah. So even more than 1 T, terabytes. Okay? Yeah. So on hard disk. Yeah. So each subarray we can load it into the main memory and get it sorted, then export it to hard disk. Yeah. All right. So you can assume after we apply our sort, we get each subarray ordered. Yeah. Then the next thing, we need to merge ordered arrays, right? Yeah. So the next step, we need to merge all these ordered arrays. That is, we need to solve this, our computing problem number 15. Merge. But when you do the merge, you need to manage your space carefully. Because you have the limitation of the size of main memory, right? Still. That means you may not be able to load two ordered arrays together into the main memory. You may not have that enough size. All right? But you can still do it. Even if you do not have, you are not able to load two ordered subarrays into the main memory. Can you do the merge operation successfully? Yes, the answer is yes. Okay? The answer is yes. Yeah. So the idea, so you need to write your program carefully. Yeah. Because you can load your data portion by portion. You do not need to load the data of whole subarray, right? Yeah. When you do the processing, each rounds, you do your data processing in several rounds, right? Each round, you just load a portion of the data from each of the two subarrays. Then you have enough memory space to hold these two portions. Then inside memory, so you can get them ordered, then you export. You export the ordered part to the hard disk, then load the next portion. Okay? Then sort it and export, and keep doing things like this. Then you can get the whole two subarrays sorted in this way. Yeah. So here you can see, every time if you load appropriate portions of two subarrays into the main memory, basically you can merge any two ordered arrays, right? No matter the sizes of these two subarrays. Yeah. Even if they have very large sizes, you can still do it portion by portion. Right? Yeah. So at the end, you can merge, all the subarrays. So you merge all the subarrays. You get a whole array sorted in this way. Think about this idea. Okay? Yep. All right. But how to merge two ordered arrays? So that's our next computing problem we need to solve. Yeah. We need to. Yeah. Yeah. Here I use this kind of special technical questions to show you. Yeah. It is useful. This operation is useful. All right. Yeah. All right. Next, so let's look at the detailed work. Now we need to do the work. Yeah. All right. Yeah. So here, yeah. So you can improve your efficiency by your computing resource. Like if you can do parallel computing, right? Yeah. So a lot of things you can do. Yeah. All right. Now let's look at the implementation details. How to merge two sorted arrays. Yeah. Given two arrays that are already sorted, how to get a new sorted array that contains all the elements. Yeah. Here we need to take advantage of the structured data. The structure, we use the order structure. Yeah. We need to use order information. Yeah. Yeah. So we need to connect to our order sorts. We have learned a few sorts, 3 sorts. Selection sort, bubble sort, insertion sort. Yeah. So we want to see which one can shed some light to our current problem, related to our current problem. Okay. Selection sort. In selection sort, do we use any order information in the selection sort? No. No matter what the order is, the selection sort always gives us the same number of comparisons. So no order information is used in the selection sort. How about the bubble sort? The bubble sort, we do not use explicitly, although there is an improved version, so kind of related to the order information, but still not very useful to our current problem. Then insertion sort. Now you can see there is a big difference related to the order information. Yeah. Think about in the selection sort, there is one big difference. Here, let me recall the result we get from the insertion sort. Insertion sort. Okay, all right. Let's compare the best case and the worst case. Worst case. There is a huge difference between the best case and the worst case. Best case, big O of n. Right? Now, big O of n, efficiency. Worst case, big O of n squared, efficiency. Huge difference, right? How big is the difference? And another thing we also need to know, under what kind of input we get a best case. Order the data. Order the data. So the best case occurs when the data is ordered. Yeah. Yeah. That's the best case. So you can see, based on this property, we can say the insertion sort takes advantage of the data order information big time in insertion sort. Yeah. So that means we need to connect our current problem to this insertion sort. to get some useful idea. All right, yeah. So now let's look at our insertion step. Yeah. We want to examine this insertion step to see if we can modify it to do this merge operation. All right. Yeah. So based on our understanding, now we need to study this insertion step another time. Yeah. All right. So we take a different view. So our old view, not related to this merge operation directly. So we want to change our view a little bit to make it related to the merge operation. All right. All right. Then we can, get the algorithm details. All right. Yeah. So let's look at the diagram. Now we want to merge one element with an ordered array. Yeah. So we have an ordered array here. Yeah. This ordered array matches one of the ordered arrays, right? Yeah. So our current data, two ordered arrays, but we have one ordered array. The other one is a single element, V, only one element. Not quite that ordered array, but it is a special ordered array, right? Single element V, we can treat it as a very special ordered array. Yeah. So here you can see our insertion step, pretty much a special case of the merge step. That's our connection. Okay? That is our connection. Yeah. All right. Then we need to recall, how do we do the insertion operation? That insertion operation could be helpful for our merge operation. The situation have some strong connection. All right. So our insertion now, very straightforward insertion, right? Yeah. So our insertion, yeah. So this time we need to connect. Yeah. So insertion we treat it as merge two special ordered arrays. The second ordered array just a single element ordered array. Yeah. All right. Yeah. So our new view. Yeah. So our new view. Yeah. So we merge two ordered arrays. The merging details should be similar to our insertion details. Definitely we need to modify accordingly, modify our insertion step to make it more general. Yeah. Because merge operation is more general than that insertion operation. So we need to do some extension. Extend our insertion operation to merge operation. That's the basic, our plan. Okay, all right. Yeah. Yeah. Next step, we want to implement this plan. All right. Merge. Apply new merge view this time. We know how to merge two arrays with special data sizes. So that's our starting point. Yeah. We start with that special case. Yeah. All right. And in this special case, data distribution not quite balanced. Yeah. Yeah. Okay. But if it's not balanced, based on our understanding, if the data distribution is not balanced, then the result algorithm usually has very poor performance. Unbalanced data would result in poor performance. Yeah. Yeah. So we want to avoid that. Yeah. So we want to avoid poor performance for the worst case. Yeah. Okay. So we want to split the data evenly to make our data distribution more balanced for the better performance. So that's our main consideration here. All right. Yeah, so by that balancing principle, when we have chance to split the data, do we have a chance to split data? Yeah. Sometimes we have, sometimes we don't have. Right. Okay? Sometimes we have, sometimes we don't have. For the insertion sort, we don't have the chance to split the data. Because when we do insertion, so that's the setting we need to follow. Insert one element into the currently ordered array. So that's the setting we need to follow. So we have no room to change it for the insertion sort. Okay? Yeah. Yeah. That's the reason insertion sort, its worst case is bigger of n squared. Yeah. So it's the performance of its worst case not good. Not good. Yeah. So you can see that's the result of the unbalanced data distribution. But for this merge sort, when we do divide and conquer, we have freedom to choose how to divide our data, right? Because nobody tells you how to split your data. You can choose the best way to split your data. Yeah. Here, we do the even split. When we split our data, we split it as even as possible. Split right in the middle. Two subarrays with almost equal sizes. For even number of elements, odd number of elements. Even number of elements, we can split two subarrays with the same size. Odd, one has one more element than the other. That kind of evenly split. Then we can avoid very poor worst case efficiency. All right. So next. We will do the merge. So C.2, merge operation. All right. How to achieve balanced, so this step is pretty easy, pretty straightforward. So here I use a simple diagram to show the idea. Okay, all right. Whenever we merge two subarrays, we make them of equal size, as equal as possible. Yeah, so even odd. Here, this is the size of the original array. When we split as even as possible. Yeah. All right. Yeah. Somewhere in the middle. Yeah. Median, near the median. All right. Yeah. All right. So there, another round splitting. Yeah. Second round, third rounds. Yeah. of splitting like that. Okay, all right. But we need to stop at some point, right? Yeah. We need to stop at some point. Yeah. Yeah. We need to stop where we cannot split anymore. We cannot split individual subarrays anymore. Yeah. If each subarray has only one element, then we have to stop. If one subarray has two elements, we can still split another round, right? Yeah. So then, stop splitting when each file contains one element. Yeah. All right. Then we can do the merge. Yeah. So we do the merge in a reverse process of splitting. Yeah. We merge two adjacent subarrays. Every time we apply merge operation, yeah. How to do merge operation? That's our next question. We will work. Yeah. Yeah, but here, let's assume we have the merge operation available. So every time we just merge two adjacent ordered subarrays. Yeah. Then another round, so we get our ordered subarrays larger and larger on their sizes. Yeah. And then, after the last round of merge, we get a whole array sorted. Whole array sorted. Yeah. Eventually, yeah. So you will get whole array sorted. Yeah. So this idea is very easy to understand. Yeah. You can see if we can merge two ordered arrays, then we can apply this idea to get a whole array sorted. Yeah. So our next question, we just merge two ordered general arrays. Must be ordered. Those two arrays must be ordered, but in a general way. We can merge them. All right, let's take a break. So then when you come back at 7 o'clock, so we study the details of merge operation.